Dear students, welcome to the next session of Design and Analysis of Algorithms lecture series. In this session, I am going to cover the traveling salesman problem. So, we will be understanding what is traveling salesman problem, how to find the solution for the traveling salesman problem using dynamic programming approach. So, this is a part in the fourth module, that is dynamic programming. So now let us understand what is traveling salesman problem. In traveling salesman problem, we'll be having set of cities. So the salesman has to travel all these cities and he has to come back to the same city from where he has started his journey. And the total the cost spent by the salesperson, in order to visit all these cities must be minimum. So that means we are going to find the shortest path or the optimal path which taken by the salesperson, optimal path. So the cost of traveling from one city to other city will be given. So we need to find out the shortest path using which the salesman can travel from one city and he can visit all the other cities, and again he has to come back to the original city from where he has started the journey. So you can see here the salesman is telling, I want to visit each city once. There are set of cities here: Los Angeles, Austin, Denver, New York, Boston, and Portland. All these are the cities. So the problem of the salesperson is he has to visit all these cities and he has to come back to the same place from where he has began his journey, and the path what he has taken, it should be the optimal path, or it should be the path for which he has spent the minimum cost. So this is a problem description. Here, given a list of cities and the distances between each pair of cities, we have to find the shortest possible route that visits each city and returns to the original city. It is usually applied in planning, logistics, and while manufacturing the microchips. Now, the modeling of the TSP, traveling salesman problem. So, while solving the traveling salesman problem, we normally model it as a undirected weighted graph. So, it can be a directed graph also, but you can see the double edges, double arrows in the graph. So that means if you consider the vertex 1 and 2, you'll be having the path from 1 to 2 as well as from 2 to 1, and the cost that you need to spend from traveling from vertex 1 to 2 need not be same as the cost what you need to spend while traveling from 2 to 1. It can be different or it can be same. So you need to model the problem as a graph in which the graphs in which the cities are the graph's vertices and the paths are the graph's edges. The path what you uh, using which you can travel from one city to other city, that is the edges of the graph, and the distance or the cost to travel from one city to other city, that is the weight or the cost of the edge. So we are using the algorithm that is given in the textbook to computer algorithms by C++, by Ellis Horowitz second edition book, and we will be solving the problem. So I'll explain you with one example how the traveling salesman problem can be solved using dynamic programming method. This is an example of traveling salesman problem. So here the graph is given. So this is the directed graph, and each edge, if you see from 1 to 2, there is a bidirectional edge. So that means there is a path from 1 to 2 as well as there is a path from 2 to 1. Similarly, if you consider the vertices 1 and 3, you have got path from 1 to 3 as well as from 3 to 1. So same way for the other vertices 1 to 4, 4 to 3, 2 to 3, etc. So, and the weight of these edges or the cost of traveling from one vertex to other vertex is represented in the cost matrix. This is the corresponding cost matrix of this graph. Here, if you see this cost matrix, so here these are the rows which represents the vertices 1, 2, 3, 4, 1, 2, 3, 4, and even the column also 1, 2, 3, 4. So 1 to 1, so that means the cost to travel from the vertex 1 to 1 is 0. Similarly, cost to travel from 2 to 2 is also 0. 3 to 3 is also 0. 4 to 4 is also 0. So the diagonal values are zeros. Next, this 10. What this 10 indicates? What is the cost to travel from 1 to 10? Sorry, 1 to 2. So what is the cost of traveling from 1 to 2? So 2 to 1 need not be same. So if you observe 2 to 1, so the cost to travel from 2 to 1 is 5. So similarly, what is the cost to travel from 1 to 3? That is given here 15. And similarly, what's the cost to travel from 1 to 4? That is equal to 20. So similarly, from 2 to 1 it is 5, 2 to 2 is 0, 2 to 3 9, 2 to 4 10. So this particular matrix, this represents the cost matrix. This is not the adjacent matrix, this is the cost, because each of the values represent the cost of the edges. Now the traveling salesman problem, as I told before, what you have to do here, given a set of cities. So here we are assuming that these vertices are the cities. Given the set of cities, a traveling salesman has to travel from the source and he has to reach all the other vertices, and then he has to come back to the source after visiting all the vertices, and the total cost of that path should be minimum. Our main goal is to find the minimum cost path. So here, source and the destination. So in this problem, let us assume that the source and the destination are one itself. So anyways, in the traveling salesman problem, source and the destination must be same. So here it is vertex 1. Let us assume it is vertex 1. So now how do we find the shortest cost path? So for that we have got a formula. So this is a formula which using which we find the shortest cost path. Now G of I comma S. So you need to understand this terminology properly so that you can expand this. So here, what does this G of I comma S indicate? So here I have written G of I comma S is nothing but cost of the path. It is the minimum cost of the path to reach the vertex 1 from the vertex I. So this is the cost to reach the vertex 1, because I have told you source and the destination both are 1. So the destination, so to reach 1, it is cost of the path to reach the vertex 1. So that 1 is not there in this terminology. In this term, we have not written 1, but it is understood that it is 1, because finally the traveling salesman has to come back to 1, because that is his source where he has started his journey. So G of I comma S is nothing but the cost of the path to reach the vertex 1 from the vertex I, visiting all the vertices in S. So what is this S? S is nothing but from the vertex I, visiting all the vertices, because here he has to visit all the vertices. He cannot leave any of the city. He has to visit all the cities. So he has to visit all the vertices. So these vertices we represent inside the set. So S is nothing but the set. So G of I comma S is nothing but it is the minimum cost of the path to reach the vertex 1 by visiting all the vertices in S. S is nothing but it is a set of all vertices to which the traveler has to visit. So that is G of I comma S. Now, how to find this minimum cost path? For that, we have a formula. What's a formula? G of I comma S is equal to minimum of Cij. So, Cij is nothing but the cost of traveling the vertex, traveling the destination j from I. What is the cost of reaching the vertex j from I? So Cij. So these values are there in this matrix. So if I take 2, 1. So 2, 1. I is 2 and this is 1. So Cij is nothing but C1, 2. The value is 5. So whatever the values that are there in the cost matrix, those are represented with the help of this C. Plus Cij plus G of, again this G of j comma S minus j. So j means what? We are considering the set of vertices inside this S. So here you see the traveler has to travel from the vertex 1 and he has to reach the vertex 1 after visiting all the vertices in S. So all the vertices are here 2, 3, 4 because all in total we have got total 4 vertices. So here j is nothing but the value inside S. J belongs to S. So you have to take one by one. First you have to take 2. So here G of 2 comma S minus J. So the inside S we have got 2, 3, 4. From that you have to subtract 1. That is J. J is what? Initially we are considering J as 2. So the remaining vertices are 3, 4. So that will be G of 2, 3, 4 inside the set. So that is how we have to replace. Now let us replace this. Now let us write what is G of 1, 2, 3, 4. Remember, this is the for this we need to get the answer because G of 1, 2, 3, 4. What it says? What is the cost of traveling to the destination from the vertex 1, visiting all the vertices in S. S is here 2, 3, 4. What is the cost of traveling from the vertex 1 to reach the destination 1 after visiting all the vertices? That is 2, 3, 4. This is what we are going to find. Now if we have to find this, we have to expand this. So this will become minimum of, I will write all the values, minimum of Cij. First we will consider this as J. So J is nothing but all the elements which belongs to S. First we will consider 2. So it is C of I is what? 1, 2. So this becomes C on 2 plus G of J is 2 comma S minus J. So this you have to leave. J you have to leave from S. So 3, 4 are remaining. So I have to write it as 3, 4. That is one value. And again J is also 3. So you have to consider now 3 as J. So C1, 3 plus G of 3, remaining vertices are 2, 4. Next the last one is I am considering 4 as J. So 1, 4 plus G of 4, the remaining vertices are 2, 3. 2, 3. Now just observe all these values. Just understand what are these values. G of 2, 3, 4 means what? What is the cost of traveling from the vertex 2 to the vertex 1 after visiting the vertices 3 and 4? That is the meaning of G of 2, 3, 4. Next, what is the meaning of this? G of 3, 2, 4. What is the cost of reaching the vertex 1 from the vertex 3? 3 is the source. From the vertex 3 after visiting 2 and 4. Similarly, G of 4, 2, 3. So for that, again, it is what is the cost of reaching the destination 1 from the vertex 4 after visiting 2 and 3. So that is the meaning of this. Now from this you can say that again these values are not direct. We don't have the direct solution for this. So what we have to do? Again you have to expand. Again you have to expand this also. Again you have to expand this also. So again you will get set of values. In that also you will be having this type of terms when you expand this. Or when you expand all of these terms using this formula, again you will have this g of that. Again that may not be having the direct solution. So you need to expand. You need to expand until you get some term for which you can directly give the solution from the graph. So that is one method of solving the problem. But here we are not following that method. We are not expanding like this. From here we are not going to expand, because since we are solving this traveling salesman problem using dynamic programming method, we are going to use a different approach. So what is that approach? So if you remember the knapsack problem, what we have done, what we did in the knapsack problem. So in order to find the in that example we have considered 4 items. Our intention was to find the value, that is the profit gain, when you consider 4 items, right? What is the total profit gained if there are 4 items and the capacity of the knapsack bag was 5. But when we had to consider that, what we did, we have constructed a table. In the table, first we considered what happens or what is a value gain when there are 0 items. That was the first row in the table. When there are 0 items, what is a profit gain? So anyways that value is 0. That was the direct sub-solution what we had for that problem. After that we have gone for the next row. In the next row we have considered only 1 item. Then we have considered 2 items in the 3rd row. In the 4th row we have considered 3 items, and in the 5th row we have considered all the 4 items, and at the end of the 5th row, that is 5th row, 6th column, we got the output. Right, so that what we did in that method is we have started from 0 number of items, then we have gone with the single item, then we have calculated the values for 2 item, 3 item, and then 4 item. So same thing even here also, we are not directly going to start in which we are going to consider all these 4 vertices. First we consider first we check from the graph, is there any direct solution available? If there is any direct solution available, we consider that, and from there we are going to build the remaining sub-solutions until we get this value. Now what are the direct solutions that is available? See, if you consider this vertex 2, you know what is the cost of traveling what is the cost of reaching the destination 1 from the vertex 2 without visiting any of the vertices. Without visiting any of the vertices means you don't have any of the vertex inside the set. So you will be having the null set. I can represent it like this: z of 2 null set. What it indicates? G of 2 null set indicates that what is the cost of reaching the destination 1 without visiting any of the vertices. Here we are considering 0 vertices in the set. Then we'll be moving on to 1 vertex, then we'll be moving on to 2 vertex, and then finally we'll be coming to this 3 vertices, and we will be getting the solution. Now we'll write what is G of 2 null set. So without visiting any of the vertices, what is the value? What is the cost of reaching the destination 1 from 2? That is C21. So this value C21. So that is equal to 5. I can directly write this as 5. 2 to 1. So this is nothing but C21, that is equal to 5. So that is one direct solution you have got. Similarly, you also know how to travel from vertex 3 to 1 without visiting any of the vertex. What is the cost? So that cost is, we represent it as 3 comma null set, that is equal to C of 3 1, that is 3 1 is nothing but 6. And next we also have G of 4 comma null set, that is what is the cost of traveling from the vertex 4 to the destination 1 without visiting any of the vertices, that is nothing but C of 4 1, which is equal to 8. So these are the sub-solutions which we can directly get from the graph. From this, now we have to build the remaining sub-solutions until we get this solution. So we'll see that how to get the next sub-solutions from this, how to use these values in order to get the sub-solutions in which we are considering one vertex. Here we have not considered any of the vertex inside the set. In the next step we are going to consider one vertex. After that we are going to consider 2, and then we'll consider 3 vertices in the graph, which will give us the solution. Okay, so in the stage 1 we have calculated all these values in which we have not considered any of the vertices in the set. We have considered 0 vertices in the set. So direct values we got from the matrix, we have written as it is. Next we'll move on to the second stage in which we are considering one vertex in the set. So we are considering G of 2 comma 3. So that what it indicates, what is the cost of traveling from the vertex 2 to the vertex 1 after visiting one vertex, after visiting 3. So we are going to find this. It has to visit 3 and then it has to go back to 1. Anyway, starting also from 1. So what is the total cost of this path? So that is G of 2 comma 3. So 2 is the source from the vertex 2 to the destination 1 after visiting the vertex 3. In order to find this, we will use the formula. So in the formula what it says, G of I comma S. So in the S we have got only one vertex, that is 3, is equal to minimum of. So anyways, minimum doesn't come into picture here. Why? Because in the set we have got only one vertex. So we'll be having only one value. So minimum is not required. So if you want, you can write minimum of Cij. Ij is C23. Ij C23 plus G of J. J is nothing but 3, comma S minus J. S is what? 3. 3 minus 3. So there is nothing in the set. So it is 3 comma null set. So G of 3 comma null set, we have these values. We have already calculated in the first stage. Now in the second stage we are making use of the values what we have calculated in the stage 1. So that value is 6. So now I can substitute C23, we know 2 is here, 3 is here. So the corresponding value is 9. So 9 plus 6 is equal to 15. So that is when we are considering the vertex 2. Now first we will finish the vertex 2. So when we consider the vertex 2, what is the cost of reaching the destination 1 by visiting 3? Now we will consider what is the cost of reaching the vertex 1 after visiting vertex 4. So that is one more value, G of 2 comma 4. You take one vertex, you consider the remaining vertices. So G of 2 comma 4. So G of 2 comma 4, again minimum of Cij is C24 plus G of J is 4 comma null set. So G of 4 comma null set, this value we have already 8. So that will become C24 is nothing but 2, 4, that is equal to 10. 10 plus 8 is equal to 18. So now we have done with the 2. Next we will take this vertex 3. Now we are considering both the cases. When it is 3, we are going to calculate the cost of reaching the vertex 1 from the vertex 3 after visiting vertex 2. That is first case. And then We are also considering after visiting vertex 4, that is the second case. Both the values you have to calculate. So g of 3, 2 and g of 3, 4. So apply the formula and calculate the value. What you will get? You will get 18 for g of 3, 2. You will get 20 for g of 3, 4. So now vertex 2 is over, 3 is over. Next we will consider 4. So vertex 4 now. Now again for 4, once we will consider what is the cost of reaching the vertex 1 from the vertex 4 after visiting the vertex 2. So here we are considering 1, that is first case. Next, what is the cost of reaching the destination 1 after visiting the vertex 3, that is the second case. G of 4, 2, G of 4, 3. Both the values we calculate, we get 13 and 15. Move on to stage 3, in which we are going to consider 2 vertices in the set. In stage 2 we have considered 1 vertex in the set. Now 2 vertices, and all the 3 cases you have to calculate. Which are the 3 cases? What is the cost of reaching from vertex 2, from vertex 3, from vertex 4? All the 3 you have to consider, and the remaining vertices also. When you consider 2, the remaining vertices are 3 and 4. So we are considering this 2 in the set. Remaining vertices are 2 and 4 when you consider 3. The remaining vertices are 2, 3 when you consider 4. So all the 3 cases we have to calculate. Now you apply the formula. So g of I, s is equal to minimum of. Now the minimum is used because here inside the set S we have got 2 values, 2 j values. Once j is 3, again the j is 4. So we have considered j as 3. So 3, and here we have considered j as 4. Minimum of these 2 values you have to consider. So minimum of C23 plus g of j is nothing but 3, comma s minus j. S is what? 3, 4 minus j means 3. The remaining vertex is 4. So I have written it as 4. Similarly, minimum, the next value is C of 2, 4. Now j is what? 4, 2, 4 plus g of j is 4, and 3, 4 minus j 3, 4 minus 4. Now 4 you have to eliminate, so the remaining value will be 3. So this value g of 3, 4, g of 4, 3, this value we have already calculated in stage 2. I am going to directly substitute those values. So that will become minimum of 9 plus 20, 10 plus 15, that is equal to 25. Similarly, we calculate g of 3, 2, 4. So apply the formula and calculate the value. For this, you are making use of the stage 2 values. You will get 25. Next, g of 4, 2, 3. So again, we will be applying the values. Once we consider j as 2, and then we consider j as. So here, once we consider j as 2, and again we consider j as 3. So the remaining vertices, once it is 3, and then next case it is 2. So what we will get? We will get the value as 23. So stage 3 is also complete. We have considered all the 3 vertices value. Now finally we are going to stage 4. So in stage 4, we are going to consider 3 cases. So we can have only one combination, that is 2, 3, 4. When you consider all the 3 vertices together, 2, 3, 4. So now g of 1, 2, 3, 4. So now 1, 2, 3, 4. So what is the cost of calculating? What is the cost of the path from the vertex 1 to reach the destination 1 after visiting the vertices 2, 3, 4? That is what we are expecting. So what is the cost of traveling from 1 to 1 after visiting all the vertices? How the traveling salesman has to visit all the cities and he has to come back to the same city where he has started his journey. That is 1. So 1, 2, 3, 4. That is equal to minimum of minimum of. Now there are three values 2, 3, 4. This we have already substituted once. So C of 1, 2. First we consider 2 as j, 1, 2 plus g of 2, comma 3, 4. Now the remaining vertices 3, 4. 2, 3, 4. From that you subtract 2. What will remain? 3, 4 will remain. So same thing for here. The third value also. So substitute according to the formula. In the S you have got 2, 3, 4. So then we will get minimum of 35, 40 and 43, which will come up to 35. This is actually the cost of the minimum cost, because we know that g of I comma s is nothing but the minimum cost traveled by the traveled from the vertex I after visiting all the vertices in S to the vertex 1. Anyways, the destination is 1. So that is what 35 is the cost of the path, minimum cost of the path traveled by the salesman from the vertex 1 after visiting all the vertices 2, 3, 4, and he has to come back to the same vertex, that is 1.